the code was essentially all models are wrong, but some are useful. So I want to open it up a bit further and want to add one word, what some are useful. But before going through that, I would like to focus on the first part of this code. All models are wrong, and especially I would like to focus on models because my job is modeling, not catwalk, but modeling 2D and 3D. And because this award was about founder scholarship for postgrad students and candidates, I would like to talk about my PhD and the achievements I had through that, the publications and the methods developed. So let's move on. We need models actually because of a very simple reason, our brain structure. Because we are always looking for new patterns, structures, and different things just to imagine and visualize everything and simplify them to be able to understand them pretty better. And in a simple way, because we have many complicated structures in nature, but we need to simplify them all to be able to remember and even analyze them and find something new in them and even develop something new in their structure. That's why if you turn around, you can see many funny things, pretty similar to someone maybe you know or you've seen through your life. So yeah, that's because of the simple structure in our brain. And to know everything better, we need to investigate them initially and find or make and generate new data layers based on what we get and understand and see or even guess from a feature in nature. As much as our data layers are complete and accurate and precise, we can focus and say our final model is more reliable. Otherwise, it's not reliable. I would go through that as well. So because I mostly work on geochemical data and geochemical anomalies and their classification, I would talk about the main errors, or some of them actually in geochemical studies. Some of them are related to the quality and variability of the geochemical data, or even our understanding about the geology of the study area, which could be wrong, which could be based on historic data, which could be quite right. Some of the errors are related to the even lab work, the chemical analysis, and some of them could be related to data analysis. But one of the main sources is actually interpolation in 3D and 2D, in both actually, because we always have a limited budget. So the limited budget results in a limited number of samples. And when we have limited number of samples, we need to find the unsampled areas values based on the sampled areas values. So we need to do interpolation based on the sampled areas. And it's a kind of estimation. An estimation is actually some error. So all these errors in different steps of our studies and analysis altogether could be prioritized as a kind of error propagation. And we need to go through them all individually and to model the final error propagation, the final uncertainty model, and even quantify the uncertainty of the final model, classified model in my field, to see, okay, if we say we have somewhere some anomaly in somewhere in our study area, how much reliable is that claim? Because in industry, they want to put money in it, and it's a big risk. So there are actually two main questions. What if we identify a sample or area that's geochemically anomalous, but this is unrelated to mineralization? Or vice versa, what if we fail to recognize a sample or area that's geochemically anomalous, but there is mineralization in the vicinity? So based on this idea, Rose et al. In 1989 proposed this table, comparing the model, the classified model we generate using any classification model, classified just between background and anomalous areas, and the geology we have, the reality we can see on the ground or underground. So we have two different parts in our model: background, anomaly. In reality, or deposit is present or not present. If we say, okay, we have anomaly and the ore is present, okay, it's true anomaly, correct decision. If we say in our model we have anomaly, but really geologically there's no ore deposit over there, is error number 2 or type 2. If we say we have some background in our model, but in that area we actually have some deposits, it's error type 1. But if you say we have some background somewhere else in our study area, and it's actually there's no ore deposit in that area, okay, that's true background. But the main problem with this interpretation is actually these two. Yilmaz and Cohen in 2017 interestingly mentioned that we can't really say we have no ore deposit in some area. It's impossible, because maybe there's something there. Maybe not now, maybe in the future. So because based on this table, oral accuracy matrix has been developed, now it's partially worked, not totally. It works only based on error type 1. So it's not that reliable. Again, let's get back to the idea I have mentioned before, the patterns. We are looking for new patterns. In nature, we see different patterns, but they're all following a kind of specific structure. I mean, if you check it out, and for example, the rivers, the streams, and blood vessels, they're all repeating each other. They're all similar, and they're repeating each other in different scales. So that's why Benoit Mandelbrot in 1983 introduced a new geometry as fractal geometry versus Euclidean geometry, because in Euclidean geometry we only have 3 dimensions of 1, 2, and 3, but in fractal geometry the dimensions could be even decimal. Also, it's based on self-similarity and self-affinity. I mean, statistical self-similarity from microscopic to continental or macroscopic scales. So if we can predict a kind of structure or feature in a specific scale, we can predict that in larger one or smaller one. Based on this idea, I mean, fractal geometry, many other methods or fractal, multifractal models in geosciences have been developed. For example, number size, which was originally developed by Mandelbrot in 1983, was also used in geosciences, for example, in exploration geochemistry, as concentration number. The size is concentration here, great concentration. Then concentration area, fractal model, concentration perimeter, spectrum area, singularity model, all by Chang et al. And their 3D formats in depths, I mean, concentration volume, spectrum volume, and number size in 3D. And at the end, simulated fractal models, like variogram and semi-variogram, because we prefer to say variogram. I use fractal here, but we prefer to say fractal, but yet it's multifractal, not fractal. So number size fractal model, for example, here, I'm not going to go into technical details, just want to clarify something to say something further. Number size fractal model is based on the inverse relationship between the number of samples and their size. In our field of work, the size is concentration. So as you see, the number of the samples with the higher concentration of, for example, gold is lower than the number of the samples with lower concentrations. Easy. And why we call this fractal model? Because if we calculate the logarithm of this equation, so we can easily find that it's an equation of the straight line. And the fractal dimension, I mean, d, would be the slope of that straight line. So we use log plots, I mean, log the logarithm of number versus logarithm of, for example, concentration of copper or gold together. Then we fit some straight line on it using least square, find the cross points, as you see here. Then as our thresholds favor and the requested or favorite thresholds for classification, and generate some classified models like this. For example, concentration area is again based on the inverse relation between the concentration and the area of the contour lines. So it says, okay, the area of the contour lines in anomalies, for example, are smaller than the backgrounds. But my first development in this field was in 2012 when I did my master thesis under Behnam Sadeghi, and I developed number size fractal model in 3D. Then we compared that number size with my supervisor's developed a 3D model, I mean concentration volume, and number size worked better in this case. But the question in my mind left was this one. Is there any new class here if I fit a new line? Because I had nothing here. I mean, the red line right here. So because I have some other black dots right here, so there must be some relation between these and these, but not in between. So a new idea came to my mind that we can come up with some solution for this one if we generate a model using more than one scenario in Bayesian framework. So I and my colleagues actually developed a simulated fractal model, actually simulated size number in 2015. And we realized that, yeah, in this area, as you see, we have a new class, at least based on the majority of the realizations. As the other part of this presentation, I'm going to talk about my PhD as well, which was about quantification of uncertainty in geochemical anomalies in mineral exploration. During this actually 3.5 years, I applied those classic fractal, multifractal models, I mean, number size, concentration area, spectrum area, and singularity model on different data sets. I would go through them as well. I would talk about them. Also, I developed some new classification models, I mean, multifractal models. But why some new models? Because I realized that in the classic fractal, multifractal models, we have a big issue. They're all, actually most of them, not all, based on geometry, mathematics actively, but then the final interpretation would be done after generating the model. I mean, by comparing the final classified model with the geology.
You have 5 minutes left.
Okay. Yeah. So I prefer to make it something active. I mean, integrate geology with the analysis. So, for example, I developed this model, concentration fractal model, and I was lucky enough to be reviewed by Fritz Achterberg in this paper. It was actually based on the classification of the target element based on its highly correlated progenesis element. The other one, category-based fractal models, including two different models for sparse data and dense data, but based on each individual bedrock. The other one was developed based on concentration distance multifractal model, which is concentration distance from centroid, which is actually based on distance between the samples and the representative point of each now mineral deposit. This actually works pretty well for somewhere when we have some kind of transformation, such as glaciers. We tried that on glaciers in Sweden. Also, in my thesis, I developed a kind of new decision-making method under uncertainty using Monte Carlo simulation, and also spatial uncertainty. I'm not going to go through that now, but also it wasn't limited to exploration geochemistry, because I also did some urban and environmental geochemical studies as well in Cyprus. And these are the results. So if you have any question about the technical details of these methods and papers, you can contact me using the email in the first slide. So let me talk about these, just two of my study areas. One, 2,500 till samples from and throughout Sweden, collected by Geological Survey of Sweden, and around 5,000 soil samples in Cyprus. The difference between these two is that actually the one in Sweden is not that dense, but it has a regular network. In Cyprus, it's dense, it's irregular. So I tried different types of data sets with different networks and to see to check all the details or errors related to the interpolations based on the different types of samples. Also, we had two different study areas, invest in Turkey based on stream sediments and catchment basins, and also some other data from Nemesis, the southern parts of the Cyprus, for that environmental study. So all in all, I generated some models. These are just some of them using simulated fractal models, using the newly developed ones, and the other ones. So as you see, the patterns are almost the same, but I'm talking about each pixel, so they're different. That's why we say them all are wrong, but could be useful. How much useful? I tried a kind of decision-making method like this. I use Monte Carlo simulation to quantify something. We call it return, and something we call it uncertainty or risk. And we looked for, or I looked for, the optimum models, because we can try it on each class per model. For example, this one is a representative example for strongly anomalous class per model, all the models. And if you look for the highest return and lowest uncertainty, so the best model could be number size, similarity, and even one of those category-based fractal models, I mean CFR. And where development should continue in the area, I mean, could be 3D formats of the newly developed models. I'm working on that. Decision making based on all the relevant sources of uncertainty, as I mentioned, those details about error propagation. And these kind of topics are actually common in petroleum engineering, but still way to go in exploration geochemistry, because we have always limited budget and limited number of samples. So it's really a good idea to go through that. And done, totally done. Just with let me say thank you so much, Peter Dowd and Regina Wendenbogaert, for organizing all these sessions. and their team actually, and Ute Muller for organizing this session, and Jennifer McKinley, the last president. Thank you so much. Actually, in her time, I got this award, and ING Award Committee, Marshall Meyer and his team, my lovely supervisor, PhD supervisor, David Cohen, and the other nominators, Vera Pawlowski-Gillan, and Nasser Medeni, Peyman Afzal, and my lovely PhD University of New South Wales. Thank you so much. And I hope we can again get along together and see each other in person without masks. And so happy as well. Thank you so much.
Yep.
Should I stop sharing?
Thank you very much. Do we have any questions of Behnam? I can't see any in the chat just now. So any questions?
Can I add something? Because I see Vera is here, and I guess probably she has an old question, I'm sure, about using compositional analysis in my research, because I have already made a promise to use that in my research. And yeah, sure. I tried different transformation, Vera, and I used a log ratio, centered log ratio, for both Cyprus data and the other one in Sweden. And yeah, and compared the results with the other transform data as well. That was the first point, start point. Hopefully in the future, some collaboration with you and even Ute and Eric and someone else.
Yeah, I'm actually not quite sure how these multifractal models work at all. In a nutshell, how do you actually use multifractals or fractals in your kind of modeling?
It's actually for classification. I can share the slide again.
So it's literally only looking at the log and using that log to to decide where to actually classify.
Yes.
And so the only way you get uncertainty then is via some kind of simulation algorithm or so.
You can use different methods. For example, for that final plot, I mean, I showed you to compare uncertainty and the return. I applied Monte Carlo simulation to each class. For example, if you, let me get back to simpler plots. For example, in this one, can you see this? Yeah. For example, this one has 3 classes, right? There are some values right here, as you see. There are some values are in between. There are some values right here. So I applied Monte Carlo to each and realized that, okay, for example, for background, which is the first group here, the left side, the return is something and the uncertainty is something. And again, I tried another method. I tried that again and to the background on that model and realized that, okay, again, uncertainty is something and return is something. Then compared all these models per class and said, okay, for background, for weak and weakly anomalous areas, for moderately anomalous areas, and strong, very strong, we can say this model has worked much better.
Okay.
It would be different case by case.
Thanks. Do we have any other questions of Behnam? Oh yeah, there is a question here. Wait a second, I'll just read it out.
6 questions.
This is from Daya Saga. Nice to hear you and meet you virtually. Many of these fractal-based power laws are useful to understand the commonly shared physical mechanism, mostly attractive to the physicists. how can these power laws really be really used in showing the basic distinction between terrains?
This is actually a nice question. We had a very big discussion with David as well during my PhD, especially for Sweden data set, because we have some kind of trends, some kind of transformation, and that's why I came up with those new ideas to resolve those problems. But still, as I mentioned, it's way to go to find a better understanding and better integration between fractal models and multifractal models and the trends in our models. Yeah, this is not just the whole thing.
Yeah. So yeah, this is a nice thing. So the question actually came from the fractal applications in geomorphology. And in geomorphology, I have seen two schools of thought. One mathematician who has done a lot of, he has derived Haust exponent, Hacks exponent, like fractal power laws. But such power laws, and there was an argument that a pure field geomorphologist is asking, all these things are very nice, and you are telling all river basins are following similar power laws and they are all of universal constants. But what is that measure which would give me to find out what is the basic distinction between the two geomorphic basins which are showing similar power laws? And that is where, the power laws were very interesting to see. From the physics point of view, it has a lot of value. But when we talk about, the core, the geosciences, and there are still arguments. This is just a kind of, observation which I've been seeing for the last 2 decades. Good to see you. They're good to hear your talk, Behnam. Very nice.
Thank you so much. Good to see you too.
Yeah, thank you very much. I must stop you now, unfortunately, but we might have time to come back to further discussions later on. It is now my pleasure to